As you can see, I will provide an introduction to reverse math, and I will try to argue or show where and how it connects to the foundations of mathematics. So there are some interesting implications there. So first, a little bit of advertising. There are 4 books on reverse mathematics, as you can see, and Stilwell's one, Reverse Mathematics Proofs from the Inside Out, is really readable for anybody almost with a high school math education. Perhaps a little more math doesn't hurt, but it's quite the layman introduction. And if you want more reverse math after this talk, you should read that one. And this is Simpson's book is the classic. Here is a successor of that, and then more recent stuff on the reverse math zoo. But that will all be introduced in due course. So some motivation for reverse math we can find in most of mathematics, in high school math, but also in the research literature. There's many informal connections between theorems. In papers or even in high school, we may say stuff like, well, theorems A and B are actually equivalent. Or theorem C is strictly stronger than lemma D. And for example, there's also a proof of theorem E without using lemma F. There's definitely historical examples. The axiom of choice and Euclid's parallel postulate are obvious examples. Most mathematicians would at some point say, this can also be proved without the axiom of choice, or this is equivalent to the parallel postulate. So there's plenty of historical examples, but those are just examples. We want a more conceptual way, a framework in which we can study these sort of things, like these are equivalent, this one is stronger than that one. And reverse math is actually one kind of framework for this study, where we can formalize these kind of statements. These theorems are equivalent or stronger, and so on. So that's a kind of motivation from mathematics for reverse math. For me, there's another motivation from logic, and this gentleman plays an important role. So you may know this guy. This is Kurt Gödel, who is famous for his incompleteness theorems in logic. Gödel namely showed that if you have a logical system T that is not extremely weak, so it can express arithmetic plus times on the natural numbers, then there's always a sentence A that can be not proved and not disproved. So the system T cannot prove A, and it cannot prove not A, assuming it is consistent, which just means it doesn't prove and
it seems that Dr. Sansandos has some internet problem. Okay, now he's here. Maybe he just drop out. Okay, is now okay?
Can you see my screen again?
Yeah, I can see your screen.
All right. Let's hope it keeps working.
Not your slide.
No, I don't see your screen.
All right. Yeah.
Okay.
Everybody can see my slides again?
Yeah.
Yes.
Yes. Very good. All right. So as I was saying, there is, I mean, the Gödel's incompleteness theorems are nice. They're quite impressive, actually, and they're famous in logic and in popular culture. But most mainstream mathematicians would say, yeah, sure, but there is no mathematically natural sentence such A. And these sentences A, these independent sentences, are purely logical. So in mathematics, they make a distinction between mathematically natural and purely logical. And since then, there's a pretty central problem in logic to find mathematically natural sentences A that cannot be proved or disproved in major logical systems. Harvey Friedman is well known for this mathematical incompleteness research, and other famous names are Paris Harrington, Jeff Paris and Leo Harrington, Kanamori Macaloon, and so on. And my motivation for reverse math is that it can provide a partial formalization of something that is purely logic versus something that is mathematically natural. That is another motivation from logic, namely this intuitive distinction, purely logical and mathematically natural, can be made more formal. Not completely, but it does work. So reverse math, it was initiated by Harvey Friedman around 1975 and developed extensively by Steve Simpson and his students and other people. At the most abstract level, reverse mathematics is a kind of classification of theorems from ordinary math based on purely logical criteria. And which criteria from mathematical logic are used? Computability, so computation. And which theorems? Usually one studies ordinary math, which means math that is about countable or separable objects. So there's always countable approximations. And this is close to the math that was done before or independent of set theory. So this is ordinary math, as mathematicians would do it, countable or countably approximable, and not too much set theory, although sometimes we touch on that. All right. So I should say a few words about computability theory. As many things in mathematics, this goes back to Hilbert. So here we have David Hilbert, and here is Alan Turing. So in 1928, almost 100 years ago, Hilbert formulated the Entscheidungsproblem. And in modern language, he asked for an algorithm that takes as input a description of a logical system T and a sentence A, and it tells you that A is provable or not. That's what Hilbert asked for. Of course, the word algorithm didn't exist yet because computers didn't exist yet. And so Turing formulated a formal definition of computability. And he formulated a formal definition of computability, which made him famous, actually. And that became computability theory. So what is Turing's definition of computability? So essentially, it's usually described as the Turing machine. It's the standard model of computability, and it amounts to a modern-day computer without resource bounds. So here we have an example. So there's a finite program, Q0, Q1, and to Qn are finitely many instructions. There's an input and an output tape, and the reading and writing head. And the instruction could be, move the head 2 places, read this cell, and write it over there. So it's a very basic operations on binary strings. And this is what Turing used to formalize computability. And people were convinced, this is the right notion. Other formalizations of computability turned out to be equivalent, but they weren't so intuitive. I'm thinking about the lambda calculus. So Alan Turing was successful. He formalized computability. And a function from numbers to numbers is then computable if there's a program that computes for every k, fk. So we put k on the tape here somehow, and then the program runs and outputs fk after finite time, as you would program on your computer. A set is then computable if there's a computable characteristic function. And of course, Turing also gave us, he said, look, this is what it means to be computable. Now I'll give you an example of something that is not computable, a textbook example, and that's the halting problem. The halting problem says, well, given a Turing machine with a certain program and a certain input, does it halt after finite time, or does it run forever? It could just it could be stuck in a loop, like normal computers. And so this is a non-computable problem. There is no computable problem of solving this. And Turing showed that any solution to the Entscheidungsproblem, so this Hilbertian algorithm, also yields a solution to the halting problem. And the halting problem is also called zero jump. So Turing showed that the Entscheidungsproblem does not have a computable solution by reducing it to the non-computable halting problem. And this was the birth of computability theory and the grandfather of computers, let's say Turing was. And later, much later, people also showed that Hilbert's 10th problem, for example, does not have a computable solution in the same way by reducing it to the halting problem, I guess. This was done by Matiasiewicz, Davis, Robinson, and Putnam, MDRP. About computing solutions of Diophantine equations. Of course, then we see, some problems do not have computable solutions. So an obvious question is, what about the rest of mathematics? How computable or non-computable is other theorems of ordinary math? And this is where reverse math gets started. So what's important is that we look at theorems from ordinary math. So it's interesting to play around with computability, but how computable and non-computable are theorems of ordinary math? And this is essentially what we measure in reverse math, how non-computable a given theorem is. So the main aim of reverse math is to find the minimal axioms A needed to prove a theorem T. And as I said, T should be a theorem of ordinary math. You should find it in an ordinary math textbook, and preferably about countable or separable things, because then we can approximate it via countable means. And we always assume a system called RCA0, which essentially gives us a Turing machine, an idealized computer. So we always assume a logical system RCA0, and we can do computable math in there. So the aim is actually find the minimal axioms A such that RCA0 prove A implies our theorem. And the axiom A, or the axioms, state the existence of non-computable sets like the halting problem, like zero jump. It could also be empty if it's provable in computable math, obviously. And now comes an important part. In many cases, almost always, we have a reversal. If we have the minimal axioms A, we can derive the theorem T, but over RCA 0, we can also derive the axiom A from the theorem T. So this is called a reversal because, yeah, normally we derive theorems from axioms in principle, but we can also derive axioms from theorems, the reverse way of doing math, hence reverse mathematics. And this equivalence precisely measures how much non-computability we need. And we will see many examples of this, but so this is why I say reverse math is about measuring non-computability. It could be provable in RCA 0, or we need extra axioms saying that non-computable things exist, like the halting problem. And then we have a precise measurement of how much non-computability we need. What is also interesting is that apart from RCA 0, the base theory, the same 4 other classes of axioms or axioms always recur. So many theorems are equivalent to these 4. And this is the main theme of reverse math, namely that most theorems of ordinary math are either provable in the base theory or equivalent to one of these big 5. There are exceptions, obviously, but it's still the case that so many theorems are equivalent to one of these 4. So they have a special place. So I should show you some computable math that we can do in RCA 0. Of course, this goes back to Turing's recursion theory and computable analysis and so on. Of course, basic properties of the reals, like if we have 2 reals, we can define the average. The intermediate value theorem is a very basic thing. If we have a continuous function that changes sign, then it must be 0 somewhere. And so this is computable. If this function is computable, then this real number is also computable. That's well known. But also analysis, like we can solve this differential equation if f is nice, so Lifshitz continuous. And this is called Picard's theorem. So there's a computable function y, which satisfies this differential equation. We can show that algebraic closures exist, so we can do basic Galois theory, but we can't show that these fields are unique. They exist, but they may not be unique. The soundness theorem of logic. If a set of formulas has a model, then it's consistent. It does not prove 0 equals 1. That's, computable. Some functional analysis even, the Banach-Steinhaus principle, if you know what that is. And what RCA 0 actually stands for, RCA stands for recursive comprehension axiom. It essentially says that for a computable function, we can form this set. It says so in a slightly different formulation, but this is what it amounts to. If we have a computable function, we can form this set. That's, recursive comprehension. And an old word for computable is recursive, of course. Essentially, you can do computable math in RCA 0. Intuitively speaking, there are some technical details, but it works rather nicely. Then the next big 5 system is Reisslemma. It's a well-known principle from combinatorics, Reisslemma, and we restrict it to binary trees. An infinite binary tree has an infinite path. And there are many equivalences from analysis. So Heine-Borel compactness, a countable covering has a finite subcovering. This is very basic, hundreds of years old. Well, more than 100 at least. And even older, Heine's theorem, a continuous function is actually uniformly continuous. That's, it goes back 150 years maybe. And theorems about Riemann integration. Weierstrass, also 100 years old, that continuous function attains a maximum. And Peano's theorem, which is about more general differential equations. So if f is continuous, not just Lifshitz, but continuous, we can solve this differential equation. And this is definitely ordinary math, because many of this stuff you will find in a first-year calculus course at the university. I learned some of this in high school even. So yeah, this is ordinary math. It's from a math textbook. As it happens, this maximum or this path, they're not computable even if the original objects are computable. Like even if you have a computable continuous function, the maximum may not be computable. So Reisslemma states that a little bit of non-computability exists, and yeah, there's many equivalences. What is more surprising is that Gödel's completeness or the compactness theorem is also equivalent. Like completeness theorem says that a sentence is provable from a system if and only if it's true in all models. But that's logic. And there's also some algebra. A countable commutative ring has a prime ideal. It's very, again, first year course on linear algebra. And so on, actually. So you got topology, Brouwer's fixed point theorem, the Hahn-Banach theorem, and so on. There's many theorems. And these equivalences do not stick to one discipline. There's algebra, analysis, logic, topology. So from the point of view of reverse math, there aren't disciplines. These equivalences just happen everywhere. And essentially, we can do some kind of Heine-Borel compactness argument in the big five system WKL0. Then Simpson has claimed that there's a connection to Hilbert's program for the foundation of mathematics here. I'm just gonna say, if you're interested in this, I can give you references. This is not undebated. I think Simpson is wrong, actually. But again, I mean, that's why we do this sort of stuff, to debate and argue whether this has some foundational meaning. Yeah. So the next big five system is ACA0, which stands for arithmetical comprehension axiom. And a formula is arithmetical if it only talks about arithmetic, if there's only quantifiers over the natural numbers. That's the only restriction. So parameters are fine, but quantifiers can only quantify over the natural numbers. The central principle is this: for an arithmetical formula, we can make this set. So yeah, arithmetical comprehension just means if we have an arithmetical formula, it gives rise to a set. Sure, why not? And there's many equivalences. For example, the halting problem that I mentioned with parameters is equivalent to ACA0. But also the Bolzano-Weierstrass theorem, another basic staple of calculus. A bounded real sequence has a convergent subsequence. Very basic analysis. And other stuff, Ascoli, Arzela, and so on. Rich enough combinatorics too, Koenig's lemma, and Ramsey's theorem, all fairly straightforward mathematics you will learn if you study mathematics at the university level. And algebra analysis. Again, there's no particular field this is all restricted to. There's equivalences from many, many areas. Definitely ordinary math. And here we can essentially do sequential compactness. So, and we observe that Heine-Borel is slightly non-computable. Sequential compactness is more non-computable because this is a stronger system. This proves WKL0. And so sequential compactness is logically harder than Heine-Borel compactness. And we have a formal way of saying that. So these are the nice and intuitive systems. The higher systems are a little bit more complicated. For example, ATR is equivalent to what I call at most one set comprehension. So if we have an arithmetical formula, which satisfies an at most one condition, then we can make this set. And this is not an arithmetical set because, yeah, here's a set quantifier. There is a subset of n. So this is already a little bit more set theory. We still have this condition. At most one y can exist. And then we can prove equivalences like countable well orderings are comparable, Ulm's theorem, Cantor's perfect set theorem, and Lucin's separation theorem. So yeah, this is again already a little bit of set theory, but this is still pretty nice group theory. So again, some equivalences. There's actually many more, but I'm just naming a few. But we get a little bit of a set theory flavor. And I'll try to explain what ATR actually means. It means arithmetical transfinite recursion as follows. So intuitively speaking, if you have an arithmetical formula, you can define this operator. So ANX defines the set gamma x. This of course exists if you have arithmetical comprehension. And you can actually iterate that finitely many times. So gamma of gamma of gamma and so on, this exists. This exists for every n, there is a set that denotes this finitely many times. We can only do this. Sure, AC0 proves this. But what is important then, it also proves that if this limit exists, it's unique. So if we take the limit as n goes to infinity or similar limits, we're not sure that it exists in ACA0, but we know that if it exists, it's unique. There's at most one limit. And yeah, then of course ATR0 is equivalent to this. Yeah, we have this condition. And ATR0 just says that, wow, this limit just exists, obviously, because there's at most one, so it must exist, essentially. So this is where iteration into the transfinite comes into play. ACA0 can do finite iterations, and ATR0 just says, oh, take the limit to infinity. It's unique, so it exists. Transfinite recursion, because, yeah, we take the limit, it's not finite iteration or recursion, it's, yeah, transfinite, because we take the limit of n to infinity. So that's transfinite recursion, and yeah, it's a kind of inductive definition too, if you want. The biggest or the strongest system is pi11 comprehension, which says that we don't need the at most one condition. We can say always that this set exists. So here's a quantifier over all sets of natural numbers, and we know there's many of those, but this set always exists. And we actually get nice equivalences. Again, group theory. It could also be that we need ACA0 as the base theory, but so an abelian group can be split into a divisible group and a reduced group, some group theory. Every tree has a largest perfect subtree, so a stronger version of Cantor's perfect set theorem, and your Cantor-Bendixson theorem, which is also nice, and some topology, determinacy, Ramsey stuff. There's of course a lot more. But as you can see, we start moving into the set theory a little bit, which is fine, because there's no hard border, of course. And yeah, this is still clearly group theory, but somehow there's some set theory hiding in there. Now, I should tell you about the foundational significance of these three systems. So, you may have heard of Russell, Bertrand Russell, and his paradox. So Russell showed that naive set theory is inconsistent. If you can do anything in set theory, you can form the set of all sets, and this leads to a contradiction, because yeah, is this set an element of itself or not? And this is well known, so we have to be careful. We cannot do unrestricted set theory. There have to be some restrictions and rules. This is Russell's paradox. It was discovered earlier by other people, of course. And what is more important is Russell's analysis. So Russell said, look, the set of all sets is a problem. It leads to a contradiction. Actually, it is an example of a vicious circle. If you want to define the set of all sets, you are already assuming this set exists because, well, the set of all sets, well, yeah, you have to quantify over all sets, including the one you are defining, the set of all sets. It's a vicious circle. To define the set of all sets, we must assume it exists already. And Russell said, this is the big problem. This cannot be. A textbook example, by the way, is pi11 comprehension, if you want something more real. So because we're defining this set, and this set, how do we define it? By quantifying over all sets of natural numbers. But yeah, we're trying to define this set, which is encapsulated in this quantifier. So, and this is what Russell said is bad. This is a vicious circle definition, which is also called impredicative. And this is rejected by Bertrand Russell, whom we have here, and later Hermann Weyl and Saul Pfefferman. And they said, well, you can't do this. Predicative math, that's the only way to go. And it should avoid impredicative definitions, no vicious circles, especially not pi11 comprehension. And so ACA0 and related systems, this is where you generally do your predicative math. And ATR0 is sort of the upper limit of predicative mathematics. This was shown independently by Pfefferman and Kurt Schutte. I should have put up a picture. So you have to imagine Kurt Schutte here, although he was not a predicativist, I guess. So this is the foundational significance of these stronger systems. ACA0 still allows you to do math without impredicative or vicious definitions, as vicious circle definitions. ATR0 is the borderline, and pi11 comprehension is the textbook example of a impredicative or vicious circle definition. So where am I going with all this? Well, I want to show you the following. If we look at the big five picture of reverse math, then we observe that mathematical theorems seem to cluster around the big five and sparse everywhere else. So here we have the big five. And as we know, well, the systems, each is strictly stronger than the next. So this is fairly weak, weak, medium, medium, relatively strong. There's plenty of stuff in between here. Purely logical formulas, like the consistency of I sigma 17 is somewhere here. But mathematical theorems, they tend to cluster. Either we prove it in the base theory or we have these kind of equivalences. And this is not absolute. There are exceptions, which we shall discuss in part 2. But it's still really nice that somehow we observe a difference between purely logical stuff, which can be anywhere, and mathematically natural things like these theorems. So, and as we've seen, each of the big five loosely corresponds to a foundational program and some kind of computability class. But the main point I want to make is here, there is a fundamental difference between logical formulas with mathematical meaning and purely logical formulas. Namely, they tend to end up in the big five. And so this is why I mentioned Gödel's incompleteness theorems, because here we see some empirical phenomenon. There is a difference between pure logic and mathematically natural. It's not absolute, but it is there. And yeah, it's pretty nice. That's why I like this field so much. So, of course, a big question we may ask ourselves is why? And why do we observe reversals? And because the starting point of reverse math is, of course, if you find the right minimal axioms, the axioms can be proved from the theorem again. There is always an equivalence, there is a reversal, but why? And I'll try to give you an indication of an answer. So there is a sociological thing. Mathematicians, they want to prove some kind of maximal theorems. You want your conclusion to be as general as possible and as few conditions as possible, because, well, you want to publish your theorem. and you want to make it as cool as possible. So maximal means very general conclusion and very few conditions. Sure, that's a valid sociological observation about mathematicians. We should look at reversals. Most reversals, a good example is the monotone convergence theorem. So that's the first reversal in Steve Simpson's book in Subsystems of Second Order Arithmetic. And if you look at this first reversal, you see, well, it's the monotone convergence theorem. So yeah, a monotone sequence in the unit interval converges. But even if you would restrict to exponentially fast sequence, so sequences that only increase exponentially fast, still the reversal goes through. So it doesn't depend on all sequences. It already goes through for the monotone convergence theorem restricted to exponentially fast sequences. But no mathematician would formulate the monotone convergence theorem that way. They would say for as many sequences as possible. Yet the equivalence already goes through for exponentially fast. That's why we always have a reversal. And so to have things that don't reverse, you have to go to sub-exponential sequences. But sub-exponential stuff, that's more computer science. I mean, P, NP, and all that jazz. So in math, you wouldn't look at this in the first place. And secondly, also this is a fairly new thing, complexity theory. And you would never formulate your theorem only for sub-exponential, exponentially fast sequences. You would just say, well, for any sequence, because it's more general and my peers will be impressed. And so this is true in general. And this is why we see reversals. It's to some extent a sociological phenomenon that people want to prove maximal theorems and that all of our proofs go through restricted to exponentially fast objects. Of course, then we still don't know why this is the case. Why do our reversals always go through for this kind of theorems restricted to exponentially fast objects? And as I said, this is true in general, except for combinatorics. And that's where most of these exceptional theorems also come from, as we will see. So first, I should tell you a little bit more about the grand scheme of things. So reverse math gives you this nice hierarchy here, but it's of course part of a bigger thing. And the bigger thing is this, namely the foundations of mathematics, the Gödel hierarchy, which is all known and natural logical systems. If you put them together, you get this nice linear hierarchy. This is ordered by consistency strength, or you could also say inclusion. And we get this nice linear hierarchy. Steve Simpson has talked about this in the Gödel Centennial volume, and others, Kellner, Burgess, Friedman, have made this observation. It's really nice. This is a comprehension hierarchy. If we go up, more sets exist, like as we've seen, pi11 comprehension, but you can go much higher. And if you go down, fewer sets exist, like here we only have recursive or computable sets. And at the top we have Zermelo-Fraenkel set theory with choice, the usual foundations of math. Beyond that lie large cardinals, as Yong Chen can tell you a lot about. And there's also historical precedent here, like second order arithmetic goes back to the Grundlagen. ATR 0, as I've told you, is the limit of predicative math. The big five are, of course, here. Hilbert's finitary math occurs in the Hilbert's program for the foundations of math. And most people will tell you that if it's natural, if it's important, it's somewhere here. Simpson has even claimed that 80 to 90% of all ordinary math can be done here. I disagree with that, but that's another discussion. And some reverse math of topology actually lives here, as shown by Steve Simpson and his student Carl Mummert. So this is where ordinary math lives. And that's really nice. I mean, it's a nice conceptual picture. As I said, I don't agree with it 100%, but it's still mostly true. So let's take a look at the reverse math zoo. So yeah, this is, I mean, part 2 is called Beyond the Big Five. Now this ZFC is obviously beyond this big five. And here we have a picture of the reverse math zoo, at least one that I could fit. Collect principles below ACA0, so ACA0 is up here. And there's all sorts of stuff all over the place. It's outside of the big five. And Ramsey's theorem and combinatorics play a central role. So as I've said before, somehow combinatorics is special because in combinatorics you can look at special cases without things looking fishy. Like you could look at Ramsey's theorem for 2 colors and pairs or this sort of thing. There's endless variations possible that still are reasonably natural. So this is the reverse math zoo can be found on the internet. I guess still administered by Damir Zafarov. And as I said, yeah, some of them are mathematically natural, but most are not. But some of the stuff in the zoo is actually nice. So there are some equivalences, like there's Vitali's covering theorem for countable covers, fairly standard math, and that's equivalent to, say, the countable additivity of the Lebesgue measure or the monotone convergence theorem for the Lebesgue integral. So there are some equivalences in the zoo, and they're even reasonably natural. Again, Lebesgue measure, Lebesgue integral, we gravitate towards set theory again. And coding becomes rather heavy. This is something I haven't mentioned because I wanted to first give you the conceptual picture, but coding becomes heavy. So what is coding? This is something I've swept under the carpet. So Friedman-Simpson reverse math takes place in the language of second order arithmetic, where there's only 2 kinds of variables, for natural numbers and for sets of natural numbers. This means that somehow you have to represent or code higher order objects. For example, a function from reals to reals is coded. Topologies, subsets of the reals, Lebesgue measure, somehow these all have to be represented via second order variables. And this can be done. And I will look at an example, coding continuous functions. So here you can see the definition of f is epsilon delta continuous. For every epsilon and x, there's a delta, such that for y close to x, if the images are close to, within epsilon. So yeah, this is something you might have learned in high school. And in reverse math, in this book, we use code. So there's this definition. A code for a continuous partial function is a set of quintuples. So I trust that most of you know epsilon delta continuity or have heard of it. And then we use this. So this is a definition via second order variables, via sets of natural numbers. Yeah, because phi is a subset of n, q, it's all countable, right? And actually, I mean, it's not entirely clear that these two are equivalent. And actually, Ulrich Kohlenbach has shown this, going back to ideas of Kleene, that these two are equivalent and that this can be shown in a weak higher order system. In fact, all you need is WKL, which is nice. Because this tells us that coding continuous functions does not change the logical strength, because WKL just tells us, oh yeah, they're the same anyway. You can work with this definition or you can work with that definition. So any theorem about continuous functions seems to be, it doesn't matter if we use codes or not. So this is, a contribution by Ulrich Kohlenbach, going back to results by Kleene more than about 70 years ago, I guess. So the real epsilon delta definition and the coded version are equivalent. And this is why this is called the good. Coding continuous functions works. And that's about it. The bad is that coding Riemann integrable functions doesn't work. So a function is Riemann integrable if it's bounded everywhere and continuous almost everywhere. So there's only a measure 0 set with discontinuities. The thing is, Riemann introduced his integral in way long before set theory in 1850. So Cantor set theory, that was 20, 30 years later. Also, Riemann showed that discontinuous functions are very important in the mainstream math. So we know the Riemann integral from high school. And we also know from university that the Lebesgue integral is superior. And it's superior because it has better convergence theorems. However, there are convergence theorems for the Riemann integral, namely this one, proved by Arzela, also essentially before set theory. If we have a sequence of Riemann integrable functions that converges to a Riemann integrable function, and these functions are all bounded, then the limit can be brought inside the integration sign. This is a convergence theorem. It's pretty old. And if you formulate it with codes in L2 in second order arithmetic, you can prove it in WKL0, even in weaker systems, actually. This is good. This is standard. This is as expected. If you formulate it without codes, it's far beyond the usual range of reverse math. It's actually close to full second order arithmetic, Z2, way beyond Pi11 comprehension. So yeah, this is a problem. Here we have a theorem that undergoes a massive change of logical strength, and it's fairly basic. I mean, it's the Riemann integral, after all. So yeah, that's bad. As I said, coding continuous functions works. Assuming WKL, we can replace codes by the epsilon delta definition, no problem. But stepping outside of continuity a little bit, it's over. Riemann integrable functions behave very differently whether we formulate them with codes or without codes. And the difference isn't small. We're talking about WKL versus full second order arithmetic. So yeah, that's why this is the bad. And we all know the good, the bad are followed by the ugly. Here's another problem. In second order reverse math, these things are rare. A splitting is when we can write A as B and C, where these conjuncts are independent. And the same for a disjunction. D is equivalent to E or F, E and F being independent. Yeah, so these are rare. There's only very few examples. And I have a paper where I find these are a couple, there's like 100 easily. There's many splittings and disjunctions in higher order arithmetic. And these things are natural. So whatever this means, this E2, which you see everywhere, this guy, just expresses the existence of a discontinuous function on the reals, which can't be coded too well, obviously. And yeah, HBU here is Heine-Borel for uncountable covers, which is old. The Lindelöf lemma or Vitali's covering theorem. These are all old theorems, and we get lots of these splittings. For example, WKL is equivalent to either Heine-Borel or there is a discontinuous function. So these things are rare, but they're not rare in higher order arithmetic. And this is exactly when we start using discontinuous functions, then we get a lot of these splittings and disjunctions. I hear a piano somewhere. Ah, yes. Right. So yeah, and this is bad because it's supposed to be rare, but it's only rare because we work with codes. And yeah, of course, we can't properly represent a discontinuous function. This is a unique higher order object. And once we have it, yeah, we get lots of splitting and disjunctions. So the rarity of this is just because there are no real discontinuous functions. And it's pretty ordinary math too. It's just higher order. You can't formulate this well in second order arithmetic. So this is why Ulrich Kohlenbach has proposed higher order reverse math. It's also in this blue book, Reverse Math 2001. I guess my copy is at the library. And his system allows for example, there's values for variables for R2R functions. And the idea is, of course, to reduce coding. And you can generalize results from second order to higher order reverse math. Like instead of talking about countable covers and sequences, you talk about uncountable covers and nets, whatever those are. And you talk about uncountable unions. Instead of the Riemann integral, you talk about the gauge integral. So, I mean, this is all too much for would be too much for one lecture. But I'm just trying to show you, look, there's this thing called reverse math. Very interesting. We see all sorts of cool stuff, but we need to do some work, namely, this coding, it's not good. We have to explore this higher order world, this third order world. And that's, what I do, to explore what lies beyond second order arithmetic. And of course, see my papers on the archive if you're interested. But first, read Stilwell's book on reverse math to get in the mood, of course. So thank you for your attention. And please read Stilwell's book.
So you finished?
Yes, thank you.
Okay, it's 1 hour, so you are expected to give maybe 30 more minutes. Anyway, okay, let's thank the speaker firstly. Okay, it's a very nice talk and we enjoy a lot. Okay, and Dr. Sanders has made many contributions about reverse mathematicals, uncountable. So for the last slide, I think it's very interesting. So if you have interest about this, you can anyway maybe just refer to his paper. Okay. Now in the following, we have enough time for free discussion and the communication with the speaker, and we also invite a commentator, Professor Yang Yue from National University of Singapore. He is an expert in computability theory and the proof theory. Okay, so in the following, first, we just give the time to Professor Yang Yue for some possible comment or questions. Okay.
Shall I stop sharing my screen or?
You can share your screen, just put here, that is okay. In case some people may have some question about some part about your slide, you can just keep the slide on the screen.
All right.
Okay. Professor Yang, are you ready?
Yeah, I'm ready, but I thought people are going to ask some questions.
First, if there's any questions, please feel free to ask.
Okay. We first give the chance to our audience. Okay. So for this next talk, so definitely I think you have some interesting part comes in your mind that you want to ask. So any question from the audience? You can also input your question on the chat box or just open the audio and ask. Anyone? Okay. Anyway, yeah, maybe student need some time to follow his questions. Okay, if no question, I first also question, and then I leave the time to Professor Yang, and then
Just a second, there's someone at my door. Come in. Sorry, I'm at the Zoom. Sorry.
okay,
Okay.
Okay, yeah, you mentioned that over RC A0, Gödel's complete zero is equivalent to WKL, right? And yeah, I'm wondering. Yeah, I'm wondering. For Gödel complete zero. So for this result, you mean the language of Gödel for Gödel's complete zero for first order language is countable, right? And yeah, my question is that if the language of the first order logic is uncountable and the corresponding Gödel's complete zero, what about their strengths under this big five? Yeah.
So yeah, there's I don't think people have looked into this because it's a very new ground, very messy business, and I don't know the answer actually. So there is this thing called continuous logic and all that, but I don't think there's a nice classification of the theorem you mentioned actually.
Oh, okay.
So there is, like, at the level of ACA0, there is some sort of soundness and completeness result for intuitionistic logic. And I mean, intuitionistic logic, of course, does not have any sort of uncountable thing going, but there are, of course, many more truth values than 0 and 1. So it's in a sense much more complicated, and that lives at the level of ACA0. Of course, it's not uncountable, but yeah.
Okay. Okay. Any other questions? Okay. There is a questions. I don't know how to pronounce the name. Okay. He asked that is there any computable sense? Sorry. Is there any computable sense in the system of higher order reverse mathematicals?
Yes. This is so Kleene. Kleene introduced a computation system called S1 to S9. So there are 9 clauses, and S1 to S8 essentially defines just primitive recursion for all finite types. So a primitive recursion is essentially iteration. Like if we have a function f, we can apply it 5 times, 20 times, f of f of f of f of f makes sense for the right types. So this is primitive recursion. And that's S1 to S8. And S9 then says, yeah, the recursion theorem holds for these clauses. So the recursion theorem is a central aspect of recursion theory or computability theory. Namely, it sort of tells you that we can sort of name a program. A program is given by a number, which we can also use as an input. So, I mean, a program is a finite list of instructions, so we can code this as a number, but we can also view or invoke this number as an input for something else. It's a kind of diagonal construction, and that's the recursion theorem. And so S9 just says, yeah, we can do this. Like S1 to S8 say primitive recursion, and then we have the recursion theorem. That's a notion of recursion for that is used in higher order reverse math. There's a more general one, which is infinite time Turing machines. So which is stronger. You have Turing machines that can run infinitely long. And that's even stronger, but yeah, that's not so useful. That's too strong. Then we're already in set theory. So there are at least some frameworks for computability theory. Yes, thank you.
Okay, so maybe you can say more about the higher order reverse mathematicals. I think maybe this is the recent work and most student or anyway, some teacher are not familiar with this. So this is kind of type theory, right? Maybe you can say more about this.
Yeah. So as I said before, well, it doesn't really matter. It's just formulated in type theoretic language for convenience. And so we have variables for any finite type. So yeah, numbers, natural numbers, sets of natural numbers, but also functions from reals to reals and so on. For those who know set theory, for any sort of finite iteration of the power set, these objects can be expressed. And it's a richer language. It's based on type theory for the simple reason that set theory explodes too fast. Like if you say even trivial things in the language of set theory, you're very quickly in a very strong system. Type theory is more fine-grained, but ultimately, classically at least, they're more or less the same. I mean, there's even constructive set theories to compensate for or complement, say, Martin Löw type theory.
Okay, okay, yeah. Anyway, multi-level type theory is also an interesting topic. Okay, anyway, maybe in the future we can have a lecture about this. Okay.
Yeah,
Yeah.
It's a little technical to say the least, but
yeah, the interesting part is about the foundational significance of this. Since some people say that type theory can be served as another foundation mathematicals. Also in your talk, you also talk about the foundational significance of the big phi, like in predicative, predicative, this kind of and finite mathematicals. I think that's very interesting. But anyway, this kind of work all has been done by many people. Okay. Anyway, okay. Any other questions from the audience? Anyone? Okay. Yeah. Yeah. In your slide, you have the RM and Zoom. In that map,
yeah.
yeah, Zoom. Sorry. In that map, the top node is RCA0, right?
AC0 is here.
Sorry,
Yeah.
AC0. Yeah. So how about the system between ACA0 and Pi11CA? So it's another map, right? It's
There are some examples of things that fall in between, but not so many. And sometimes it very much depends on the formulation. So a famous example by there's some famous examples by Antonio Montalban. So which are part of what is called hyper-arithmetical analysis. So they are just above ACA0, but they are stronger than ACA0. Julien's theorem, I'll type it in the chat, is an example. So, or maybe with double L. So it's about countable linear orders. But then, of course, yeah, the question is, what do you mean by a countable linear order? And this is also where the coding comes in, because a countable linear order in second order arithmetic is given by a sequence. But so there can be a difference between a countable set and a sequence, because it's very hard to prove, actually. This is what Dachnoman and I have been working on. It's very hard to prove that a countable set of reals can be given by a sequence. And so this is why we go into higher order reverse math, because these things can be very different when we say that a countable set is the sequence, like in reverse math, or if we just say, well, countable set, like given by an injection or a bijection to the natural number. So these two are different, and that's what we're exploring.
Okay. So you think that in this map, you think that some systems are not comparable, right?
Yeah. So there's so the main source is that Ramsey's theorem, like here, for example, Ramsey's theorem for pairs and two colors, and many variations and special cases and so on. This is somehow different from WKL. But again, this is Ramsey's theorem, so we can color countable sets, infinite countable sets. But what if this is countable sets given by a sequence? What if we use normal set theory definition? Countable set of reals is subset of, say, the reals, and there's an injection to n. Then we see this picture is very different. So some of this picture definitely depends on the formulation, namely all objects, all sets are given as a kind of sequence. But a countable set does not have to be a sequence, actually. And so then the zoo is a lot. We have another question.
Yeah.
So there are big five in higher reverse math, and so they actually here we have this is almost this picture almost tells you that. So in second order reverse math, Heine-Borel for countable covers, that's just equivalent to WKL. And then there's the associated system is the same thing, but about uncountable covers. And monotone convergence for sequences, that becomes monotone convergence for nets. So there are big five in higher order reverse math. And essentially they're the same theorems, but generalized to the uncountable. That's so. For example, theorems about Riemann integral generalized to theorems about gauge integral. So there is a big five in higher reverse math, and essentially they are similar, but they talk about the uncountable. This kind of stuff.
Okay. Yeah. We have the same in the question. Yeah, it's just exact big five or big six, big seven.
So Vitali's. So people have said that sort of Vitali's theorem gives you the big sixth system for countable covers in second order reverse math, and in higher order reverse math. It's Vitali for uncountable covers. And I should note that Vitali himself talks about uncountable covers in his original paper about where he introduces Vitali's covering theorem. So there's a big sixth system. So based on Vitali's theorem for uncountable covers. So this Vitali's covering theorem has some nice equivalences. And if we look at uncountable case, then that's maybe the big sixth system.
Okay. Yeah, so it's very interesting that the same theorem, if formulated with code, and then maybe it's very weak. Strength is a very weak system, but if without the coding, it's become very, very strong. So very interesting. Yeah. Okay.
Sorry.
Please. Okay.
I wanted to say the theorem about the Riemann integral is sort of the best we have at the moment because it's so basic. The Arzela's convergence theorem. I mean, it's known maybe for some time. Yeah, James Hunter, yes. So James Hunter, as you can see in the chat, he wrote a PhD on reverse math, higher reverse math, and he showed that coding topologies is problematic. So coding topologies doesn't work so well, and so but nobody was so surprised because it makes sense to some extent. Like topologies are very well. Topology is supposed to be independent of the cardinality mostly. And so, but then that coding that you can't properly code topologies, okay, sure, why not? But so we go to a new level of simplicity because we can, this theorem is old and very basic. This is much more ordinary. This is really ordinary math compared to, say, topology. So we're quite proud of this, Dag Norman and I. So yeah, this is joint work with Dag Norman, of course. I should have mentioned that.
Okay. So any more questions? Yeah, you can ask via audio or just input your in chat box. Another question from Shu Changjie. Does constructivity play a role in higher order reverse mathematicals?
So that's actually a very good question. We sometimes see the same problems and challenges as constructive math. So how to say this? As an example, the reals are uncountable. Is if you formulate this with the set theory definition, so there is no injection from the unit interval to n. This is quite hard to prove. It's actually it's implied by this convergence theorem for the Riemann integral. So the reals are uncountable in the usual way, follows from this theorem. And so it's very hard to prove. But this is also the case in some strands of constructive math. So in some parts of constructive math, the reals, it's consistent that the reals are countable. Namely that there is a bijection from the unit interval to n. We can never list all the reals, but we can, it's consistent that there is a bijection from the unit interval to n. And this is true in constructive math, and this is true in higher reverse math too. Other things, so oftentimes we can learn a lot from constructivity. We don't directly use it, but it's often kind of inspiration.
Okay. And any more questions? Yeah, maybe a general question. So what is the scope of the higher order reverse mathematicals? It is up to ZC?
We shouldn't go like I would say higher order reverse math should stay not go beyond this level. So if we can prove it, so there is of course higher order versions of Z2. I would say higher order reverse math is everything that lives below that. We shouldn't go beyond this level, say the medium range, as it were, is where we should stay. The strong range is more set theory, perhaps.
Anyway, maybe a silly question. So why it can't reach the level of Z3? So you mean just below Z2, right?
Well, we have no interesting things that require Z3 at the moment. So in higher order reverse math, I mean, we can write down some sentence from set theory, as you know, like like in your research in set theory. But if we write down theorems of ordinary math, usually we do not go beyond this level. So that's again, maybe if we look with more people, we can find something that goes to the level of Z3. But at the moment, we don't know such a thing.
Yes, my PhD thesis is related to this.
But that's set theory, of course.
Yes, we can find a sentence expressible in Z2, but it cannot be provable in Z3, but it can provable in Z4. So from your comment, you mean that this cannot be done with higher order reverse mathematicals?
Well, I don't think we can reach that. We like at the moment it's hard to reach. We can reach pi12 comprehension. That's actually the highest we can go at the moment. So, and yeah, some things, but not so natural, can reach up here. And so, yeah, Z3 is very, very far away for us still. So we at the moment we can go up to here. I mean, with nice things like we show that Bolzano-Weierstrass for countable sets, countable with the usual definition with injections, that can get us up here, pi12 comprehension. But we don't know how to get to pi13 comprehension, for example. So yeah, even full second order arithmetic is kind of hard to reach.
Okay, is this the reason that you doubt whether the Gödel hierarchy based on the comprehension is the right scale to classify objects? Yeah.
Well, that's more because we get, like, for example, we get this problem, like these splittings and these disjunctions. So there are the Gödel hierarchy says there's one linear hierarchy, but in higher order reverse math there's always two kinds of things, namely either a theorem implies the existence of a discontinuous function, and there's many of those, or not. So, and Heine-Borel for uncountable coverings does not imply that there's a discontinuous function. So here essentially in the splitting we see that reflected, and so we should use two measures: one for comprehension and discontinuous functions, and another measure where we don't have discontinuity around. And so my main motivation is this kind of thing. Like, once we have discontinuous functions, we always have to have two scales: one where there is discontinuous functions, and the other one where everything is consistent with all functions are continuous.
Okay, that's interesting. Okay. Okay. Any other questions? Okay. If no, now we leave the time to Professor Yang Rui to give some comment or anyway questions. Okay.
Okay, thanks, Sheng. So Sam, can I share the screen with?
Yeah, sure. I'll
okay. So I will make 3 comments or 2.5 comments. So the first one is I'm going to echo Sam's main theme. We are going to do some advertisement for reverse mathematics. So here's a paper by Richard Shore. It was okay. You can see the preprint was in May 2010. It was published at a Bulletin of Symbolic Logic in the September issue of the same year. So you can see that this is based on his Gödel lecture at ASL Logic Colloquium. So the theme was reverse mathematics. Okay, the title is Reverse Mathematics, the Playground of Logic. So in this lecture, Richard Shore is trying to promote the interesting area, research area, reverse mathematics. So I'm not going to okay, if you are interested, you can read the paper by yourself, but I will sort of show you a few paragraphs, and some of them are related to Sam's lecture. Okay, so okay, so I'll show you. Okay, so here, so on this page, problem 2.2. It says develop a computability theoretic type of reverse mathematical analysis of mathematical theorems on uncountable structures using whichever generalized notions of computability seems appropriate to the subject being analyzed. So from the dialogue you just had between Cheng Yong and Sam, you can see that they are, okay, it's a very interesting area to push the reverse mathematics to uncountable structures. So in this paper, Richard Shore mentioned, for example, in order to do this, in order to study uncountable reverse mathematics, you have to develop, perhaps you have to develop a computability theory which is beyond omega, beyond natural numbers. So he mentioned alpha recursion and other generalizations of computability. And Sam just mentioned infinite time Turing machine. So it is a new territory to us. Although the paper Richard Shore was written in 2010, I believe until now there's not much progress. Maybe one of the big progress I heard is Doug Noman and Sam Sanders. So they developed this higher, so-called higher reverse math. So actually, I was I want to ask Sam actually to elaborate a little bit more about what kind of system they are using. So maybe I will show you the rest of the Richard Shore's paper, just probably one more paragraph, and then Sam can tell us a little bit more about what are the systems of the behind the higher type, behind the higher reverse mathematics. Okay, so okay, so in the next few sections, Richard Shore mentions the four major branches in mathematical logic. You can see number 3, this is a proof theory, Sam's area. Okay, so I will not show you what's going on. And then recursion theory, so it's my area, and Richard Shore also work, I mean, he is my supervisor, and so we are working in this area. And okay, this is, okay, after Sam make comments, I will say a little bit more about the zoo if we have time. Okay, so this is part of the zoo. Okay, and then you can see model theory showed up here, and then set theory and stronger system. Probably I don't know whether that at that time higher reverse math was popular or not. Okay. And then the last thing I want to show you is this conclusion from Richard Shor's paper. So he says, we have tried to paint a picture of reverse mathematics as intimately involved with all the classical field of mathematical logic. So, which is proof theory, recursion theory, model theory, and set theory. So, of course, by the nature of its subject matter, it also deals with most areas of classical mathematics. As a playground, then, its playing field are large, right? There are many kinds of games to play and a wide variety of equipments. So I urge you to come in and join the fun, right? So this is Richard Shor's message. I guess this is fit the theme of Sam's talk. So I'll stop share. I don't know whether, okay, so my next remark will be on the zoo and Ramsey theorem, which is my working area. But I hope to hear from Sam about a little bit more about this higher. For example, in your in the last slides of your lecture, you also there's a Z3 showed up, right? So there, I wonder what are the systems, how you maybe earlier people asked questions whether there's still big five or other things. Are there typical subsystems of higher reverse math, or that's also my question. So Sam, I don't know whether I'm clear or not.
Yeah. So I didn't want to include this in my talk so as not to overload the audience, but so let me show you one picture. All right. If I can share screen, wait. All right. So, is this visible to all?
I can see it.
Yes.
Yes.
So here on the left, we have the big five with some equivalences, many equivalences. And so there's actually a higher order generalization in higher order arithmetic. So, for example, on the left here, we have Denis theorem, which is equivalent to Heine-Borel for countable covers. And then on the right, we have a similar equivalence, which is much harder to prove, however, Denis theorem for nets and Heine-Borel for uncountable covers. Similarly, here theorems of the Riemann integral exist, and these are equivalent to theorems of a much more general integral. The gauge integral is even more general than the Lebesgue integral. And some basic stuff like here AC0 is equivalent to the range of a function exists. Here we have some kind of, this is Pfefferman's projection axiom. It's equivalent to the range of a third order object exists. So all these sort of countable second order things on the left can be generalized to third order things on the right. And if we then apply the ECF translation, so ECF is a syntactic translation. It replaces uncountable objects by reverse math codes. So yeah, I mentioned reverse math codes. So actually, this is where they come from. Before reverse math, Kleene already introduced what he called associates or representations, and these are reverse math codes. And this is a way of mapping higher order arithmetic into second order arithmetic. Just throw away everything, replace all the uncountable third order stuff by second order reverse math codes. And actually ECF converts the right hand side to the left hand side. So all these theorems about uncountable things, they become the theorems on the left if you throw away all the third order stuff. So there is in fact a big five in higher order arithmetic, and it's a similar development, but it's a very nice one because how do you generalize sequences? Well, this is known from topology. That's called nets. How do you generalize beyond the Riemann and Lebesgue integral? Oh, that's known. It's the gauge integral. Heine Borel for uncountable covers was formulated 130 years ago and stuff like that. So why should open sets be countable unions of basic opens? Why can't they be uncountable unions of basic opens? And that's what happens here on the right. You lift the restriction to second order arithmetic, and you get a generalization of the big five. And if you want to go back, you apply ECF. ECF was formulated 70 years ago by Kleene. So there is a big five, and it's actually the second order big five are only a reflection under ECF of a higher truth. That's the way it is actually. And I mean, the thing is, of course, this requires a lot of knowledge from the audience, like what's a net. Most people don't know what a net is. The gauge integral is also mysterious. But so here you have it. The higher order world is a generalization of the second order world in this particular instance.
So when you lift say from type 1 to type 2, when you lift one type, do you increase does the model increase one cardinal, or it goes from aleph naught to 2 to the aleph naught, or to aleph 1 or something?
You have to make, you have to make your models a lot bigger, of course, but I mean, for example, your models are a lot bigger, but at least what you said,
Okay. Okay. Yeah, I'm happy to hear this.
Yeah. And so, well, this is not the entire story.
Okay.
So this is just one part. This is like we have lots of stuff flying around, and this is Arzela's theorem, for example, and there's lots of stuff, and we're still very much investigating this, but that's I mean, this is there's a lot of strange stuff out there, but if you want a nice clean picture, then this is nice. There's the big five of reverse math, and there's also the big five of higher order reverse math, and higher order generalization in the most mundane sense possible of math, because as I said, from sequences you go to nets, from the Riemann integral you go to the gauge integral, and so on. So
Okay. Any reference for this? You have a survey paper on
the one I submitted to JML.
Okay. Uncountability OR, or
exactly. That has. Oh no, not true.
No, okay.
Well, so there's two papers. They're both on the archive. I'll write it
Okay.
in. I'll write it in the chat. Yes. So chat. I can't access the chat somehow. So I'll send it to you.
Okay. Thank